must say it's a great privilege to be here, to be chosen for Red Paper at the Royal Statistical Society, and credit for that really goes to my co-author, so I'm going to let him do most of the talking today. But first, I'd like to explain how we got here and share some of the background to the work that Mathias will be presenting. So this collaboration comes out of a workshop at the American Institute of Mathematics that took place 5 years ago, which brought together statisticians and algebraic geometers to talk about model selection. And there's a list of participants there. So today's speakers are in bold, as you can see, but also I'd like to acknowledge the organizers of the meeting, who are in italics: Russell Steele, Bernd Sturmfels, and Sumio Watanabe, about whom I'll say a little bit more in a few minutes. So this meeting was very enlightening for me because it focused my attention on an issue that I'd previously ignored, and that's the issue of singular models. A statistical model is singular if there are parts of the parameter space where the Fisher information matrix is non-invertible. And there's a list of several common classes of models there that are singular, but the general heuristic rule is right at the bottom. Any model with hierarchical structure is quite likely to be singular. Now, if you're fitting a reasonably complex model in the 21st century, it's quite likely that you're using some kind of hierarchical structure, and therefore singular models are something that you should be aware of. So to illustrate basically give a basic introduction to singular models, I'm going to use this very simplified two-component Gaussian mixture model, where the observations are drawn from a normal distribution with mean mu, with probability alpha, and mean minus mu, with probability 1 minus alpha. And I've simplified this model so that there are only two parameters, and I've done that so that it's easy to represent the parameter space on a slide. But obviously the same issues apply in higher dimensions as well. Now, I've prepared a couple of demonstrations using Shiny, so I'm going to try and switch over to that now. Here we go. Right, so here I'm representing the probability density function of this two-component mixture model in this dynamically generated graph. And on the left, I'm afraid you can't read the text, on the left are two sliders that I can use to change the parameters of the model. So here I'm changing the mixture probability parameter alpha, and by sliding that up and down, you can see that I'm changing the probability weight given to the two mixtures. And I can also change this other slider here, which brings them either close together or further apart. And I can even animate these as well. So this is showing what happens as the probability weights move from one mixture to another. And this one shows what happens when the mixture components are brought together and then further apart. And as you can see, I've stacked the two densities, so what you see, the total that you see, is the marginal density. So changing either of these two parameters will change the probability density function in general. However, if we superimpose the two components there so that they have the same mean, so that mu is 0, something different happens. In this case, changing the alpha parameter does change the mixture weight of the two components, but it doesn't change the overall density. And what this means is, in effect, we've lost a dimension from our model. Now, the asymptotic consequences of that are quite severe, and I'm going to demonstrate that in my next Shiny demo. And this is a demonstration using some data that are simulated from this model. And I've started by just simulating 10 observations from a model with a parameter mu of 1, so the two components are separated, and a probability weight alpha of 0.5. So the probability weights are unequal, but they're very close. And on the right-hand side, what you can see is the likelihood surface in this two-dimensional parameter space, which is represented in two ways. On the top, there's a perspective plot of the likelihood, and on the bottom, there's a filled contour plot of the log likelihood, where values below -6 are not shown. Those are censored. So the likelihood surface doesn't look like much, but here we've only got 10 observations. However, by clicking this animation, you can see what happens as the number of observations increases from 10 up to 100. Now, the first thing to say is this is a mixture problem, so it inevitably suffers from the label switching problem, which gives us a multimodal likelihood. And in particular, the whole likelihood surface is symmetric if you rotate it by 180 degrees. But apart from that well-known problem, the likelihood is behaving very well as the sample size increases. The maximum likelihood estimate is converging towards the true parameter values. The likelihood is concentrating around the maximum, and on the log scale, the likelihood surface can be well approximated by a quadratic surface. So that's all very good. However, if instead we were to simulate some data from the point where the two mixture components are superimposed on each other, where mu equals 0, then things look very different. Now, the sample size has been reset down to 10 again, so I can rerun the animation showing you what happens this time as the sample size grows from 10 to 100. So the likelihood surface appears very different. Although it's concentrating along the direction of the axis mu, its behavior along the axis alpha is very different. There are large fluctuations, and the final form in this case is a ridge shape. And actually, things are even worse than they look. Down here, I can change the seed used by the random number generator. So just by changing that, I can show you all the possible shapes that you might see from a random sample of 100 observations here. And you can see a wide variety of different shapes are possible. But what they all have in common is that the likelihood along the axis mu equals 0, which is shown by the dotted line on the bottom plot, the fill contour plot, the likelihood is constant along that, because that is the point where there is the singularity in the model. So that's me done with the shiny demo, so I'll close that. So what this means is that if your asymptotic theory relies on your maximum likelihood estimate being bivariate normal, then you're in trouble. And in general, if you're relying on the likelihood being a quadratic surface around the maximum, you are also in trouble. And this is where Sumiya Watanabe comes in. He basically reformulated the foundations of asymptotic theory for singular models. And he did that by using algebraic geometry, and in particular relying on the Hironaka's resolution of singularities, which won Hironaka a Fields Medal in, I believe, 1970. Now, Watanabe's theory applies equally well to regular and singular models, and for that reason he tends to use the adjective widely applicable for the results that he derives. This work was developed over a decade in the early 2000s, and it's summarized in this book, Algebraic Geometry and Statistical Learning Theory, which is an extremely dense and concise book. The theory is explicitly Bayesian, and it is the language used within the book is the language of machine learning, which is perhaps an additional barrier to the dissemination of these ideas within the statistical community, unless you are a habitual reader of the Journal of Machine Learning Research. So I do think Watanabe deserves to be more widely known than he is. Now, before I hand over to Mathias, I can't say a lot, obviously, about singular learning theory, but there is one aspect of it which I found fascinating at this meeting at the American Institute of Mathematics. That's that there are two distinct concepts of dimension emerge from singular learning theory: the singular fluctuation and the learning coefficient. Now, the singular fluctuation, represented by the Greek letter nu, shows how strongly the posterior distribution fluctuates under repeated sampling, and the learning coefficient shows how fast the posterior distribution shrinks with increasing sample size. Now, in regular models, which is to say models where everything is nice and quadratic, asymptotically. These two quantities are the same, and they are both equal to the dimension of the parameter space divided by 2. But they are different quantities for singular models. Now, the singular fluctuation is not the topic of today's talk. Today we're going to be talking about the learning coefficient, which is accompanied by an integer quantity called the multiplicity as well. And the multiplicity is 1 in regular models, but can be higher for singular models. Now, it turns out to be extremely difficult to calculate what the learning coefficient and the multiplicity are. And there's really only a handful of model classes for which these values have been calculated exactly. Nevertheless, one of the things I hope that we can persuade you today is that insights from singular learning theory are still applicable when you don't know exactly what these quantities are, but you can still provide good bounds on them, and they can still be useful. So I think that's all I have to say, and now I'm going to hand over to Mathias for the rest of the talk.
So this is about a particular proposal for how to define an information criterion that is Bayesian inspired for singular models where you have that issue with non-invertible Fisher information matrices. Okay, cut off a little bit the top there. But okay, so I'm going to condition on us all being very familiar with Schwarz's BIC. And just to remind you, so this is about considering as a model selection score criterion the log maximum likelihood, and subtract from that a penalty that's given by counting the parameters of the model divided by 2 times log n. And I want to start with a numerical example here to show you where exactly does this come from, what does Bayesian and Bayesian information criterion mean. And so this is a simulation about a mixture model, so similar to what Martyn had, a little different the setup, so I'm going to consider mixing 2 Gaussians with both variance 1 and unknown means mu1, mu2, and a mixture weight alpha. And that's the model that I'm considering. And I'm going to generate particular data. And I'm going to begin by generating them from an honest 2 mixture, that's a 40-60 mixture of a normal with mean -2 and variance 1, and a normal with mean 2 and variance 1. And here's what I'm going to do now. So I'm going to over and over again generate a sample of size n from this data generating distribution. Once I have that sample, I'm going to compute the integrated likelihood function under a prior. I'm not going to talk about it for now. But it's so maybe I should say it's a uniform on alpha, maybe I should say that. And then Gaussian priors on mu1 and mu2. Okay, so generate data, compute the integral of the likelihood function. That gives you a number. I'm going to store that. To make it comparable across different samples, I'm going to take that integrated likelihood function and divide it by the likelihood under the true data generating distribution. So I'm going to call this the marginal likelihood ratio. And then I'm going to do this over and over again, and I believe 200 times at a sample size of 50. I average the values that I get for this marginal likelihood ratio after taking the log and multiplying by 2 for convenience, and I get this point up there. Then I'm going to do the same thing again at sample size 60 instead of 50. And I get this point there, and I keep doing it at sample size 70, 80, 90, 100. And so on the x-axis I show you the sample size on a log scale, and on the y-axis I show you this doubled up log marginal likelihood ratio. Now if you think about a linear relationship, right, in Schwarz's criterion there is this linear relationship sitting around there, number of parameters. I'm doubling it up, so number of parameters log n. So if you think about a linear relationship, well, let's fit a line through these points. So if you fit a line through these points, a least squares line through these 6 points, then you get this solid line here. And superimposed and dashed, I have a line in which I do a least squares fit with the slope constraint to be -3, so minus parameter count. And so they line up nicely, and so I would claim that this is sort of a numerical illustration of what this asymptotic theory that underlies Schwarz's criterion. Okay? So this 3 in Schwarz's theory is a 3 because there are 3 unknown parameters, alpha, mu1, and mu2, and therefore I'm integrating in R3. Okay? All right, so that's nice and good. So what is our paper about? So our paper is about the following. If I change the data generating distribution, things may turn out different. So I'm going to change the data generating distribution to not be an honest 2 mixture anymore, but just a single normal that I take to be normal 0, 1. Okay, and here's what happens. So back and forth a little bit. Okay, so you get to follow your visual impression because the meaning of a tick mark is still the same. It's a 0.5 change on the y-axis, and the x-axis is the same in any case. So it's the exact same plot repeated. The only thing I've changed is how did I generate the data. And now that slope is all of a sudden about minus 1.5 in the least squares line, and there's the theoretical support for 1.5. Okay? So if I thought that the 3 before was due to 3 parameters being involved in our model, then this model now seems to be in the Bayesian, in the spirit of Schwarz's paper, it seems to be a model with 1.5 parameters. Okay? So there is some form of an effective dimension for this model that depends on how the data are generated. And now this relates back to the illustrations that Martyn showed you. Because if you think about this normal population, right, how can I represent it as a member of this model? Well, I can pick the mixture weight alpha to be 0. Then I have to pick mu2 to be 0. But then mu1 is free. You can choose it whatever you want. And vice versa if I pick alpha to 1. But I can also set the 2 means equal to each other, and then the mixture weight becomes free. Equal to each other and 0. And then the mixture weight becomes a free parameter. So in that sense, at this data generating distribution, the parameterization is not 1-to-1. It has an infinite dimensional pre-image, right? A one-dimensional pre-image, which is a union of 3 line segments. And somehow, this affects the integral, as you can imagine, and somehow the asymptotics even, and that slope becomes 1.5. So what our paper is about is this. So in these singular models, this is what happens, right? So this non-identifiability has to lead to a non-invertible Fisher information matrix, right? There's 3 linearly independent directions. It'll be the 0 matrix, the Fisher information. And the usual theory that we do, quadratic approximations and so on, is no longer there to give us this result of 3. Something else will happen. Some more refined analysis is necessary to get at figuring out what the slope is, and it is 1.5 at this in asymptotia. Okay, and so our paper is about the following, right? Schwarz's information criterion is inspired by a measure of model complexity that is effectively the slope of this line that I'm fitting. Okay? And in regular models, the slope is always determined by a parameter count. And we've gotten very used to applying this all over the place, right? The resulting criterion. But in these singular settings, it's not the parameter count necessarily. And it can be 2 different things based on what the data generating distribution is. And therefore, you're left with, all of a sudden, in this example, 2 different versions of BIC, depending whether you think it's a single normal population or whether you think it's a 2 mixture. But deciding which one is the case, that is the model selection problem that prompts us to look at this in the first place, okay? So you're in a situation of circular reasoning. Okay, so this is what the paper is about. And I'm going to just introduce some notation from the paper. So we're looking at this information criterion that comes out of a mixing frequentist and Bayesian thinking, or thinking in a frequentist way about Bayesian model choice. So in Bayesian model choice, we're looking for posterior model probabilities. So M is sort of my model indicator here always. Yn is a sample from a distribution, and this is a posterior probability for a model, and this is proportional to prior model probabilities times the integrated likelihood that we denote P of Yn given M. And so, practically speaking, these models will be parametric that we're looking at. They're indexed by a Euclidean parameter omega that ranges through some parameter space omega that will be a subset of Rd. And the integrated likelihood function is this integral here. I have a likelihood function, the likelihood of data Yn under the distribution indexed by parameter omega, and that is being integrated with respect to a prior on omega. And now, so in Bayesianism, this is a number that you calculate from the observed data set. Now I'm going to mix in frequentist thinking and think about what does this do once I make data random again. So I'm going to think about yn being an n sample from some distribution pi 0. That I'll take to be part of the model here. And then this becomes a random variable. And I get a sequence of random variables as I change the sample size. And the behavior of this random variable depends on what pi 0 is potentially and how large the sample size is, right? And what's in Schwarz's work and other follow-up that firms up these arguments is that if the prior is nice, so let's say it's everywhere positive and it's bounded, no poles, it's not zero in important places, something like that, then in nice models, nice means the same niceness that you use to prove asymptotic normality, this sort of quadratic expansions are making sense. You get a result that there's an asymptotic expansion to this marginal likelihood, that when you put it on the log scale and you retain only the terms that are not of bounded order, you get to see that the log marginal likelihood is equal to the log of the maximum likelihood minus d over 2 log n. D is the count of parameters here in this model, and then plus a lot of stuff that we're going to sweep under the rug and say it's a term that's bounded in probability. Okay? And the nice thing, and you can analyze this term more, but the nice thing here is, so this is a quantity in which the data generating distribution is not visible, right? So this happens in lots of asymptotic things we do. Somehow the dependence on the data generating distribution drops out, and then we have something that we can actually calculate in statistical practice and we run with it, right? And so this is the PIC. Can you do anything, Martin? Just click into the slides. Oops. Okay. If you want to prove this theorem, you'll have to do quadratic approximations. But as Martin said, we're going to be interested in models where this isn't always possible, right? Because the Fisher information is not invertible. A quadratic approximation will not capture potentially anything, right? If it's the zero matrix, the Fisher information. And this happens in models like Martin mentioned, mixture models, factor analysis, whenever you have rank constraints on parameter matrices and so on. Now, this is my favorite example of an integral that you have to think about in this sort of context, okay? So the marginal likelihood, of course, is an integral. There's randomness involved, and that's an additional complication. But at the heart of the math of working out what an analog to this parameter count is studying Laplace integrals that could look like this. So I can give you an example where studying this becomes relevant. So you can see that somehow we've maybe gone to fourth order approximation, and you're supposed to integrate the exponential of minus n x squared y squared. I want you to think of x and y as parameters in a statistical context. Okay, so our job is now to figure out how does this change as I vary n, this integral. Okay, and this is an example of a singular Laplace integral because the function up there, it's Hessian, right, is not invertible. So you can do this by hand, right? Using properties of the Gaussian CDF and integration by parts, you can actually work out by hand what this is. And you'll see that this is minus 1/2 log n plus log n plus a constant that I could work out plus a sequence that goes to 0 as n grows. So if this was related to a marginal likelihood, right, then the model that this comes from is a model with 2 parameters because I'm integrating in R2. And it turns out that its behavior that you get from this beginning of an asymptotic expansion looks much like this 1/2 log n, looks like a 1 parameter model, right? So its effective dimension is then like 1 instead of 2 parameters, right? And even the log n makes that an overstatement, right? And it turns out that this is the sort of thing that you see more generally, and this is so in a framework where you commit to some assumptions of likelihood ratios being suitably analytically dependent on parameters, you can prove that even when you have singular Fisher information matrices, there is an analog to Schwarz's theorem. There is an asymptotic expansion that you can do in which if you only retain the most crucial parts, you get this type of a formula that says that the log marginal likelihood, even in settings with singular Fisher information, equals the log maximum likelihood under some assumptions. And then there's some log n term and maybe a log n term like you see in this example plus stuff that's bounded in probability. But as I tried to highlight here, what exactly these coefficients in front of log n and log n are, this may depend on what the data generating distribution is now. And that'll be in the cases that we're going to look at, effectively boiled down to, is pi 0 a distribution in which the parameterization is finite to 1, or is it infinite to 1? Right? And if it's infinite to 1, how is it infinite to 1? That'll determine these coefficients here. Okay? But, okay, we can say a lot about this, but at least we're in a position now that is statistical trouble, right? Because it's no longer true that when I retain just this most crucial of pieces in this beginning of an asymptotic expansion, it's no longer true that this is free of knowing the data generating distribution. It's not. It's like in my example that I showed. The slope can be -3 or -1.5, right? So it can be 3 over 2 or 3 over 4 here, since I don't multiply by 2. And then, what is our information criterion? Well, there's sort of a version that I should contemplate if I knew that it was one mixture. It was a mixture of a single component. No mixing, a single component, right, in my beginning example. And then there's a different version of the information criterion if I think that the truth is that it's a two mixture, right? So that is not statistically practical. So here's just an example of what numbers like this can look like. So this is about reduced rank regression, which is a model in which I'm putting a rank constraint on a matrix of parameters in multivariate regression. I here is my symbol for what the rank that the model postulates, and J is my symbol for what the true rank is, so the rank of the true matrix of regression coefficients that I contemplate here. And first point is, it is not true that this function here, lambda of pi 0, is not a continuous function or anything like that of the data generating distribution. Right? Of course, finite sample behavior varies continuously with a data generating distribution, but these asymptotics, they do not. Right? This is not a continuous function, which prevents any sort of reasonable plug-in estimates here. Plugging in stuff for pi 0 is not going to get you in a good place. Fortunately, it depends only on certain aspects of the data generating distribution, right? And so in this example, when I think about a model that postulates that some matrix of parameters has rank at most 3, okay, this is prior dependent, but I don't want to go into too much detail. These learning coefficients, they only depend on the rank that you see in the true data generating distribution. They don't depend on any other feature of the data generating distribution. So if you work out all the theory for this, you get sort of a triangle of numbers out, right? Where you see things like, okay, the model with for rank 3, somehow it becomes more Bayesian complex as the truth becomes more complex. So if the truth goes from a 0 matrix to a rank 1 matrix to a rank 2 matrix to a rank 3 matrix, these coefficients in front of the log n, they increase. And also, if I fix a true data generating distribution, if I look at more complicated models that allow for higher rank, these numbers go up typically. So if they behave in a reasonable way, that can affect the dimension. Okay, but so at the time of the meeting that we had, the starting point was we knew all these numbers at that time, but what do you do with it? And, how is this statistically useful? So at that point, it's really just an illustration of how maybe BIC isn't capturing the behavior of the marginal likelihood. So we discussed this at this meeting, and then this is what started this paper. Okay, so how might we use mathematical knowledge of this type? So we'll have a finite set of competing models in our setup that are indexed by some index I. Called MI. Fortunately for us, typically the smallest of all models is a regular one. So for example, in the mixture model setting, there's the model where I don't mix. It's just a normal distribution, unknown mean. So that's a nice regular model. There's no doubt about, there's no multiple different approximations and so on. It's easily handled. And then furthermore, there are typically generic values for these guys. So it's typically the case that if I contemplate model I and look at its marginal likelihood, if I want to study it under data generating distribution that's taken at random from model J, then there will be a fixed constant value for these learning coefficients, as we call them, as well as their multiplicity, the log n constant. And so this is the framework that you see. This is what you see happening in practice in these mixture models and other cases. And what that means now is that there's sort of a finite number of possible approximations. We're going to call them Lij prime. And Lij prime, you should think about, this is the sort of BIC that you would form if you base yourself on the asymptotic information about model I when generating data from model J. Okay? A submodel Mj. And so in terms of this previous slide here, so we have in a way, as I consider, let's say, the model corresponding to rank at most 3, I have 4 different approximations, okay, that I could contemplate. Now, what can we do with those different approximations? Which one to use depends on an unknown truth, right? What we're proposing in the paper is to consider averaging them. Okay? So how might we average them? Well, if we stay true to this Bayesian thinking, we might want to think about, we want to maintain our model uncertainty, right? When I think about model MI, and when I think about 3 mixture components, I don't want to commit with certainty that there are 3 mixture components. I want to allow with positive probability that there might be only 2 or only 1. And so, in order to express this, we looked at turning to posterior model probabilities to use as weights. So we're going to try and weight different approximations by posterior model probabilities, right? So as I think about model I, for all its submodels indexed by J, I have different approximations Lij prime. I want to weight them by posterior model probabilities, so they capture sort of my Bayesian model uncertainty, right? What I think about model Mj. Now, if I write this out in a different way, more explicit, the posterior model probabilities are proportional to the marginal likelihood times prior model probability. See that there? Then you look at this and you say, this is totally ridiculous. Because I want to approximate a marginal likelihood using a weighting scheme in which I pretend to know the marginal likelihood, right? So if I could actually compute the right-hand side, I would never even think about forming the approximation on the left. But, okay, as we toyed with this long enough, at some point we came up with the following idea, and that is to simply define things by themselves. So we're going to think about this approximation that we want to form, and we're going to use that approximation itself to define it, right, on the right-hand side. In other words, we're going to build a fixed point equation system in which the approximations that I want to form ultimately, they're used twice. Yeah? They appear here on the left-hand side. That's where they are defined. But they also appear on the right-hand side in order to define them. Okay? Now, all that means is that, okay, I get a rational equation system in some unknowns that I want to solve for. There's one unknown for every model in this equation system. It's a rational equation system. If I clear denominators, I have a higher degree polynomial system. And this could be very bad for us, right? But the way we set things up is, in our averaging, we always only contemplate the given model and other submodels of it. And because of that, this becomes a triangular system. And it becomes a triangular system that has the nice feature that as you solve it along, starting from the smallest model to more complex models, you always only have to solve a quadratic. And that quadratic will have a unique positive solution, which is nice for us because we're looking for probabilistic quantity. And therefore, at the end, this big old fixed point equation system has a unique positive solution. And we're going to call that our proxy for the marginal likelihood. And to make a connection to BIC, we're going to take a log and call that our singular BIC. And yeah, I don't know, maybe if it's not intuitive, you just sit down and do this for an example of mixture components 1, 2, 3. And then you see it in action. But okay, so this is our proposal. And it generalizes BIC in a sense that if a model is regular, then all of these approximations are the same. And you can do whatever weighting you want, you just recover the usual BIC. Okay, so we have some consistency discussion, but I'm going to just skip that. I just want to point out that through our construction, we're able to get sort of an analog of we want to get the result that we really want. We want that for any true model, the marginal likelihood matches our criterion on a log scale up to a bounded remainder. Okay? So that was the point of the exercise, and we get that. And I want to take a few minutes to show you some stuff in action. So there's an application to reduced rank regression where you see things like this. So blue is BIC, red is our criterion. The truth is a rank 3 matrix. And BIC, it's based on the parameter count. That's the largest possible complexity you could give it in this Bayesian sense. And it tends to always under-select here in these types of applications. And our weighted averaging leads to a little bit softer of a penalty and I think quite reasonable frequentist selection properties. Okay? And yeah, so here at the end you see that at sample size 300, there's a little bit of uncertainty left whether it's true or 4 components for our criterion. BIC, okay, is not that certain that it's that the rank is 3. Sorry, not components, right? Okay. We've also included some experiments on, do we capture Bayesian model uncertainty? Okay. So we took a data set from Lopez and West, and it's a larger data set, and we subsampled. So we created random subsamples at different sample sizes, and then we computed using Markov chain Monte Carlo techniques. This is of course subjective as can be. Some Bayesian posterior model probabilities. Depends on what particular priors one uses and so on, of course. But just sort of give an illustration. So we adopted priors that they used in this paper, and we computed posterior model probabilities over many subsamples, and what they come out to be is illustrated by these box plots. And then you can use these BIC type quantities to define approximate posterior model probabilities, and this is what they are if you use the usual Schwarz way of parameter counting, and this is what they are for our criterion. And as I flip through this, I hope that you appreciate that the spread in the left and the right panel are somewhat similar, whereas in the middle panel, the posterior probability very quickly is essentially always 1 for 2 factors. So what I want to express with this is the left and the right panel, right? They have a similar way. The way uncertainty gets resolved through increasing sample size is similar in our criterion in the fully Bayesian method. In the middle, the BIC is just too aggressively narrowing in on the simplest structure of 2 factors, which ultimately is what we concentrate on, but the way uncertainty gets resolved is similar in our proposed method and the Bayesian method. And I only have a few minutes left, so maybe I'll conclude with 2 minutes left. I conclude with this picture. So there's a lot more going on, so I have not emphasized yet the role of priors, for example. But priors can be very important. So in a mixture model, this is sort of a similar situation to what my numerical experiment was about. So there's some example we put in a paper on binomial mixtures. And what I'm illustrating here is I'm thinking about a single binomial distribution with a success probability of 2/3. And I think about how can this be represented as a member of a 2-component binomial mixture. And then you see what I said in the beginning, right? You can reproduce this guy by picking alpha, the mixture weight, to be 0, and then one of the success probabilities becomes a free parameter. Or you can do it the other way around, and the other success probability becomes a free parameter. Or you can set the success probabilities equal, and then it becomes the mixture weight becomes free. And in those sorts of settings, it becomes very important, and we're grateful for the referees for pushing us on this, but it becomes very important to be precise about what does the prior do? How much prior mass is assigned, let's say, in the neighborhood of the endpoints of 0 and 1, okay? This becomes crucial, and it becomes crucial in a way that it's reflected in the asymptotics, okay? And so as we discuss things, and this becomes more pronounced as you mix multi-parameter distributions, because these gray lines, they start to become planes and three spaces and so on as I mix higher dimensional component or multi-parameter component distributions. And so a whole bunch of experiments in the paper about this issue as well, and we're making some concrete recommendations using bounds, like Martyn said, on these learning coefficients, where the bounds are merely based on the geometry and geometric features like the dimensionality of these pieces in this pre-image of the parameterization of the model. And I think I'm well advised to stop, I guess, right? So maybe I'll do that now. But to conclude, let me say we have an R package now that implements all of the models that we exhibited, and here is the reference to Sumi Watanabe's book. And in our lectures here, we tried to give a softer introduction to that. Not sure it's very successful. And I include one reference because all the examples I give you are total order, number of mixture components, number of factors, rank, and but there are other applications where it's not a total order, totally ordered that set of models by inclusion.
Okay, it's a pleasure for me to be here and discuss the paper we just heard about. Okay, I want to go to the next slide, please. We just heard about the singular Bayesian information criterion, and in this paper, the authors took a really big step to leave the comfortable area of parametric models where everything is nicely defined. Fisher information matrices are invertible, and they started out from trying the traditional Bayesian information criterion consisting of two parts. First part is the maximized log likelihood, and the second one is counting the number of parameters, multiplying it with the log of the sample size as a penalty part of the criterion. And actually, as we've seen, both parts of this criterion bring you into troubles when you apply it to singular models. You cannot simply count your number of parameters anymore, and to obtain the maximized log likelihood, you want to go via a quadratic form involving the inverse of the Fisher information matrix. And what's really nice in this paper is that the authors gave a full treatment of the problem. They did not just fix one or two of these parts of the BIC, but they went back to the underlying motivation behind the BIC and came up with their singular Bayesian information criterion. And going there was a long way, a difficult way. They went via singular learning theory. We heard about the problem with the learning coefficients that show up in that theory. Problem is that they depend on the true data generating distribution, and when you want to do model selection, that's of course a problem. You cannot assume that distribution to be known, because otherwise you would not have to select a model in the first place. But by defining a fixed point equation system, they came up with a clean and easily interpretable definition of their new model selection criterion as BIC. And I also like this paper because it opens up perspectives for many further research directions into areas that so far were too difficult to tackle, and I want to give you one such example. The example I want to retake is one that's written in the paper, where factor analysis is illustrated to study changes in exchange rates for different currencies. Several models are proposed. One of the models is selected by the singular Bayesian information criterion, and people could use that model for many different things they want to estimate, such as, for example, changes in exchange rates from the British pounds to the US dollar, or from the British pounds to the euro. And people could have different time horizons in mind. For example, 1 month change 1 month ahead difference in exchange rates, or a 1 year ahead difference. So when we think about model selection, it's unlikely that if we want to predict these 4 things, that one model would do fine. One model would be optimal for all 4 predictions. So what I think would be an interesting topic of further study is to go into more details about some focused view of model selection, where you want to say first what you want to predict, then find a good model for it. And this is what we call focused information criterion. The way it's currently defined and applied, it's not applicable at all to such singular models, because people would state the focus, say the loss function and want to minimize, and then select a model that minimizes that loss function. And most of the time the mean squared error is used, and both bias and variance depend on the inverse of the Fisher information matrix. So I think it would be very interesting to start with the given theory and try to come up with a kind of focused version of the information criterion, but it won't be easy, I think. People might want to start looking at different loss functions and mean squared error, for example. And there are many other interesting aspects about this SBIC. The fact that it's phrased into a Bayesian setting is nice, because it automatically takes the model selection uncertainty into account without really having to do many difficult things which you would need to do in a frequentist setting. And thinking about that, I think the value of SBIC could form a nice basis to construct model weights that could be used in a frequentist setting as well for model averaging. What I also found nice was that the SBIC has the same consistency properties as what we are used from studying Schwarz Bayesian information criterion, and at the same time it does not lose its connection to the large sample log marginal likelihood. And these aspects, I think, might also give possibilities to develop further theories for hypothesis testing. It was not the goal of this paper, only a model selection was treated, but I think there might be interesting links there to do too. So in conclusion, I liked reading the paper a lot. Find the paper very interesting. It gives many opportunities for further thought and work, and therefore it's a real pleasure for me to propose the vote of thanks.
It's a pleasure for me to be here, and I forgot, but actually, so this is a joint discussion with Christian Robert from Paris as well. Next slide. Right, so maybe it would be easier if you do, yes, one more step, one more, and that's fine. So just to summarize the setup, so you're looking at marginal likelihood as a way to do model selection. And the general theory in regular model tells you that you have the approximation with the BIC. In other words, the log of the marginal likelihood is like the log likelihood at the MLE minus this dimension dk over 2 log n. And in the regular framework, it really comes from the fact that the log likelihood is asymptotically quadratic. And so this dimension comes from that, and I'll come back to it afterwards. In the irregular models, you cannot have this approximation anymore. And then, because the Fisher information matrix is typically non-invertible, and so it doesn't work the same. A typical example is the mixture models, which you have seen in the talk, but there are others that were discussed before. We can go down because it would be easier than me asking you all the way through. And so the way I sort of tend to think about these problems, which I think it might be slightly more intuitive than looking at the algebraic geometry approach, is to understand the log likelihood more like, so the log likelihood at the MLE plus the log of the prior mass that you have of Kullback-Leibler neighborhoods of the truth of order 1 over n, say, okay, over n. And one of the advantages actually to go in that direction is that you can extend it to high dimensions, which you cannot with the other ones. But apart from that, what happens is that in regular models, the Kullback-Leibler neighborhoods are like quadratic neighborhoods. And so the prior mass of these quadratic neighborhoods is like the volume of a Euclidean ball, and so you get this dk over 2 that pops into this prior mass. But when you are in irregular models, then the geometry of the ball is not like a Euclidean ball anymore, it looks different. And essentially what you're trying to do is to find some path that have like the smallest possible path in your prior, such that you can approximate your truth in terms of your Kullback divergence. And in the mixture models, for instance, you can approximate by having one of the alpha, the weights that goes to 0, or you can merge the components, and these two ways have different prior masses. And essentially, the effective dimension, or the learning coefficient, comes from finding the sort of sparsest for the prior. And that's sort of the story. But so that was my story. But it's a bit crude compared to the Watanabe's formula, because I never thought about this MK plus P naught term, so this multiplicity that comes into the log n that you could capture using algebraic geometry. The advantage of the crude version is that you can extend it to high dimensions and very, very general framework. Next one. So what happens is that, so using this Watanabe's formula, you've got these two terms, the red and the blue, and then and you have to assume, so it starts from, that's the starting point of the story, that these functions from P naught to lambda k of P naught are known. So these learning coefficients as functions of the parameters are known, but you don't know the parameters. You don't know where you are. And so you have to estimate them, and that's where their contribution is quite nice, is because they have this sort of very clever approximation, not really of the coefficients themselves, so the learning coefficients, but they approximate directly the marginal likelihood with their algorithm. But one of the sort of strange aspects of it, although it's not so disturbing, I think, is the fact that by having to approximate this quantity, the approximation doesn't depend only on the model K itself, whereas the marginal likelihood depends only on model K, but it depends on the whole models. And so if you change your class of models, then you have to restart the whole approximation story. But that's a minor point, I think. So the question is, why should we care about something like that? In particular, why should we care about the BIC? So the BIC from a frequentist point of view is a penalized likelihood, and so it's another version of selecting models. And then if you're purely frequentist, then maybe the BIC is not the best option, because there is this paper, the nice paper by Elisabeth Garcia and Ramon von Handel, that says that you could actually go down to a penalty that's log n. And if you have a smaller penalty, then the separation rate of your tests, if you think of them as tests, is better. And so you should go, if you're purely frequentist and you want to be optimal, then you should go to the smallest possible penalty, and it's not the Bayesian approach. It's not the BIC story. Second one. But it's the advantage of the BIC is that you have a completely off-the-shelf kind of procedure, and you can put it in any software. You don't have to think about it, essentially. That's what's nice compared to the log n story, where you would have to compute, to calibrate somehow the constant in front of the log n, and for the moment there is no theory on that. Another thing is that you might want the BIC because it has a Bayesian interpretation, because it's an approximation of the marginal likelihood. But in this case, why don't you just use the marginal likelihood? And so that's the question, why don't you just use the marginal likelihood? There are typically two answers to this question. The one answer is that if you use the marginal likelihood, then you have to specify the prior on the parameters, and then people don't like it because some of the priors can be very influential, and you have to be careful about it. I think it's maybe down the page, and then it would be easier. I think there are 5. Yes, maybe one more. Yes, yeah, thank you. I think it's a sort of a fake argument. It's just an argument to be lazy and not to have to think at all. The reason why I think that is that the BIC is purely asymptotic. Now, obviously, because the BIC is an approximation of the marginal likelihood, asymptotically the prior disappears. And so if you're worried about the impact of the prior, then and you're only thinking of the BIC, you're only thinking asymptotically, and asymptotically the prior disappears. And so you don't have to worry about it. And so in this case, the question becomes, for finite n, is the BIC better behaved than just a basic marginal likelihood with a prior that's not too bad, but that's not marvelous? And that's my first question. Typically what you could do if you want to calibrate the prior is to choose a data-dependent prior. So, and then you have a calibrated prior, and so the marginal likelihood would be better calibrated to some extent, and you wouldn't have to resolve to purely asymptotic results. So this is all about BIC, not the SBIC. The reason why it becomes even more crucial for the SBIC is that the theory, which was not said in the talk, but it's said in the paper, the theory is only valid if you have a compact space. And if you have a compact space, then you can use non-informative priors, typically. Most of the non-informative priors, thank you, in compact spaces are proper, and so you could use the non-informative priors, and so the choice of the prior in this case disappears, essentially. So the second argument, which is the true argument, is that it's much simpler to implement. This is true for the BIC. In most models, the MLE is done in algorithms that you can find in softwares, and so it's easy to compute. Thank you. Just maybe down the page, and then I remember what I have to say. That's nice. But here still it's quite not complicated, but the algorithm is slightly more involved because you have to simulate from some kind of posterior somehow, and so it's not such an off-the-shelf. So you're losing the off-the-shelf property. Again, you have to think about it, and you're using the off-the-shelf property moreover because you have to first find these lambda k of p naught as functions of p naught. So it's not an off-the-shelf property method anymore, although you can implement it for some families of models. And also, typically you can have upper bounds on the lambda k of p naught, but you don't. It's very hard to get the right values. So upper bounds might be better than the basic decay, but compared to the real value, is not so good. And as Mathias was saying at the end of his talk, you're losing the capacity, the ability to actually choose your prior such that you're targeting, which is what he was mentioning at the end. You can just sort of target your prior on some of the, for instance, on alpha, to make sure that alpha sort of shoots off to either 0 and 1. And then if you do something like that, then the posterior has some kind of behavior asymptotically, which makes it very, very nice and interpretable. And with this SBIC, because you don't have a prior, then you are not able to do that anymore. Still, I was supposed to be the nasty guy here, but still, this algorithm is amazingly simple if you think about it, and so that makes it a very elegant approach. And I think that's about it I wanted to say. I think, yes, if you go down. No, there was something else, thank you. I have 1 minute or something? Yeah, thank you. So that just to sort of throw a stone in the pond, if I may. So marginal likelihoods are tools to do data exploration. So you have families of models, you do data exploration, you want to select a model. So the question is, are there right tools? And so somehow everybody uses them, or they use some, but can't you do something else? And the reason why you might want to do something else is that these are just numbers, and marginal likelihoods as numbers, they don't mean anything unless you compare them somehow. And the question, and beside that, they are just a number, so it's a very crude approach of data exploration. And so instead of having just numbers, you might try to go through data exploration procedures that actually explore posterior distribution, the entire posterior distribution. There are some nice works that are done by Chris Yao and Chris Holmes using different loss functions, and so they explore the posterior using interrogating or using different loss functions. And then yes, thank you. You could also use different priors, and so you're exploring the posterior distribution using families of priors, and that's what we did with some students for mixture models, for instance, trying to understand the number of components doing something like that. You could enlarge your models and put mixtures of mixtures, if I may say, and then in this case you have parameters alpha j that tells you which model you could be in. And then you have a whole distribution on the alpha j that gives you more than just one number. And that might be ways of exploring what you want to do if you want to do data exploration. Thank you. And so I was supposed to say one sentence to say that I second the vote of whatever. I'm delighted, whatever. I'm delighted.
Okay, so it is my great pleasure to be here and to give a comment on SBIC. Okay, so SBIC is very interesting and it is very powerful by our numerical experiments, but it has a limitation here. So to calculate SBIC, we need to know the learning coefficient or at least upper bounds. But under some assumption, there is a trivial upper bound, which is a dimension over 2. But so if we do not know learning coefficient or non-trivial upper bound, then we have to use d over 2 as a lambda. So practical use of SBIC coincide with BIC, which is no longer criterion for singular models. So before giving the proposal, let me introduce notation. So let IWBIC epsilon to be defined as right-hand side. So we note that if we set epsilon is equal to 0, it is a WBIC by definition of WBIC. So it is a little wider class of WBIC. Okay, move on. And by using two IWBIC epsilons, we can construct a consistent estimator. So if we have two IWBIC right at the bottom, then this is an example how to construct consistent estimator. So our proposal is if we do not know learning coefficient or non-trivial upper bound, we propose to use the SBIC with a consistent estimator as above. Okay, move on. And another proposal is to use improved WBIC. The reason to use improved WBIC is performance of WBIC for some models are not quite good. So we'd like to improve the one. So the optimal inverse temperature of the IWBIC is okay. So there is a uniquely optimal epsilon star that holds the equation, and epsilon star in WBIC is said to be 0, but we propose a different one. The different one is the following estimator. Okay, move on. So we compare the performance among them, and we think the data generating model is Gaussian mixture with 2 components, and all parameters are assumed to be unknown, so variance are unknown. And candidate models are Gaussian mixture with at most 3 components, and we run 100 experiments with sample size 200, 500, and 1000. So here is the result. So the left-hand side is sample size is 200, and the blue one is BIC, and orange one is WBIC, red one is SBIC, and the green one is SBIC lambda hat, and purple one is IWBIC. So when sample size is 200, then SBIC and SBIC lambda hat works well. And when sample size is 500, that's same. SBIC and SBIC lambda hat works well. And when we have sample size 1000, then SBIC, SBIC lambda hat, and IWBIC works well. So to move on to the next. So the summary of the simulation is if we know the sharp upper bounds of learning coefficient, then SBIC performs well. And also SBIC with the estimated learning coefficient lambda hat, then we have almost same performance as SBIC in our experiments. So the point is SBIC with lambda hat, we do not use any knowledge of learning coefficient. We estimate it. So it is very widely applicable. And also, if we have large samples, then IWBIC is an choice, could be. Yeah, that's all. Thank you.
So, good afternoon. I'm here on behalf of Niall Frail and Chris Oates and Tony Pettit from QUT. Next slide. So we particularly enjoyed the paper, so thank you for that, Marius and Martyn. So the sophistication of modern statistical methods demands intelligent approximation methods, and this is definitely a step in the right direction in that sense. So please, next slide. So at present, we only really have 2 options for singular models. You've got SBIC and WBIC. So SBIC, you need these analytical bounds on learning coefficients, and the prior is used implicitly in the way it's worked out. WBIC, it's more general if you can afford the MC cost, and it combines approximation and computation. It requires Monte Carlo, but approximation is used to reduce this. in the case of exact methods, and the prior is explicitly used. So please, next slide. So in the paper we saw that it was demonstrated for the case of rank selection that the performance of WBIC was inferior to SBIC. The reason was not discussed, and I'm not going to have a reason today, but we have some results to share from a publication to appear where for everyone's favorite model, the Gaussian mixture, 2 components, we found that the WBIC for low sample sizes was having this systemic bias. So if we had 100 independent data sets with n equals 50, we would see the WBIC would always tend to overestimate the evidence, whereas when you increased n, you wouldn't get that same result. And we're interested to see if that was the case for SBIC as well, whether this bias occurred at low sample size. I know WBIC is this approximation, asymptotic approximation. SBIC is not in the same way, computed in the same way. So please, next slide. So, and just to summarize, so that in section 6.2, it does not indicate that SBIC overestimate the model for Gaussian mixtures. We're interested to see if that's the case. And in figure 4 for factor analysis, it said that SBIC is not overconfident. So in a different class of problem, that overestimation wasn't occurring. It would be interesting to see if that was happening for that model as well. And just like to finish with, so Tony and Niall and Chris in particular were saying it was a very thought-provoking paper. So thank you.
We have received 4 reports so far. Don't forget you can send your own discussion in the next 2 weeks. The first report is from Professor McLaren and Dr. Nguyen from University of Queensland. And they discuss specifically the case where you have a mixture model with an arbitrary number of components. What actually they do is that they say that basically that a way to make the likelihood of a mixture more well-behaved is to integrate out the alphas, and then they mention some results for specific class of mixtures. And I'm not sure exactly what this is getting at. Maybe they're saying that from this you could build an alternative criterion for model choice based on these remarks. So I'm sure the authors will have a better idea than I do about this. The second discussion is from Richard Charnigo. So Richard Charnigo is from University of Kentucky, and he has 2 questions for the authors. The first question is related to the fact that when you take 2-component mixtures, if you assume that mu1 equals 0, then you have a different asymptotic regime. You can see at the middle it says that the conventional rate goes from 1/4 to 1/2, and he wonders if your criterion could be adapted to such a case where you have a different asymptotic regime because some parameters are known. How will you adapt your criterion? So that's the first question. The second question is related to the fact that SBIC, what is specific compared to BIC is that depends not only on the model you consider, but also all the other models, right? That's a property of SBIC. And so this discussant is wondering what happens if you would apply SBIC to a first subset, for instance, mixture with 1, 2, 3 components, and then you will try to extend it to 4, 5, 6, and then 7, 8, etc., etc. So is it possible to use SBIC in this way, considering a sequence of subset of models? And we move to the third discussion. So this third discussion comes from Spain and Italy by Elias Moreno, Walter Acuño, and Laura Ventura. And these people have several concerns about the paper. The first concern is that the fact that SBIC is based on the Fisher information, whereas they think that Fisher information should play no role in the base factor, because the base factor is not defined in any way based on the base Fisher information. The second point is a bit long, but I think they're taking issue with this, actually, the last equation. So in the last equation defines this posterior distribution condition on the fact that the model is either I or something before or something smaller. So in a mixture context, condition of fact you have 1, 2, or 3, if I could be 3 components. And they're saying, I think what they're saying is that's not a proper posterior distribution. And if you go down, they also complain about this one, but I wonder if maybe there's some problem with their notation because I don't see the connection with the previous one. But anyway, they take issues, I think, about the fact you use this kind of nested posterior, pseudo-posterior distribution, if I understand correctly. And they also have a third concern about the fact that even if you're in a regular class of models and when you use BIC, there are settings where BIC is not consistent. So what they're saying that it might be also a problem for SBIC. We could have a class of models where SBIC cannot be consistent because BIC will not be consistent anyway. Or should I say for similar reasons? Right, then we go to an email sent by someone called Longford from, what is the institution? I don't have Imperial College, sorry. Nick Longford, sorry for that. So after the first positive sentence, we have, I hope that my negative comment will not dampen the anticipated enthusiasm of the authors and readers. And so again, this person has some issue with the approach here. So let me summarize that through 3 points. I think the first point is the first paragraph. Even if the appropriate model has been selected in particularization, we have to take into account the other models that would have been selected in replication. Being a Bayesian does not absolve anybody from attending to this intractable problem. So I guess this is related to the fact that should you do a model selection or model averaging, or should you do something else? This is a rather large and broad discussion about what we really need to do when we have a model uncertainty, which is of course a big topic by itself. The second point is starts with the ubiquitous reference to asymptotics is another drawback. And then he makes an interesting point about the fact when you use asymptotics, you really look at trying to find the model with the best fit, because in the limit you have infinite data, so you can perfectly fit if you have a true model among consideration. But I think what this person will rather want to do is to choose a model that may be wrong, but that give you, for instance, good forecasts or things like that. So I think he's a bit against the idea of using asymptotics for this reason. And then in the end, this idea of model averaging goes back a little bit in a slightly different form. Then he says that actually we could go further, and for a single data set, one model may be efficient for one estimate, and then you have another estimate, you want to use another model. So he recommends that we abandon the search for the best model or best combination of model and explore to combine a set of alternative estimators. And quite conveniently, he cites his own paper where he did that in linear regression. And this is it. Again, if you have any thing you want to contribute to this discussion, remember you have 2 weeks to send anything to the Royal Statistical Society. Thank you.
So, but a lot of interesting things were said. To start off, the BIC, I think in some ways the way it's used is a bit of a state of paranoia, right, or schizophrenia. You're sort of, you want to be Bayesian maybe, but not too Bayesian, and you maybe don't want to show a prior, and so I think some of the appeal is from apparently being prior free, which in our setup isn't actually quite as true as Judith also mentioned as in the regular case. And at the same time, so this can have appeal, but then it could also be something unappealing to somebody who really wants to do Bayesian analysis. So I think, in my opinion, it's a bit of in a schizophrenic place. It's interesting meeting place of different ideas, but it's also, if you work on a particular data set where you have the time to really tune Monte Carlo methods and compute a marginal likelihood, and you can think about priors, why not, right? And I don't think there's necessarily a reason to turn to something like what we've done. But as I tried to do numerical work for this paper, it's surprisingly hard to find people willing to put computer code out there for computation of a marginal likelihood that's being used by someone other than the researcher developing that code, and maybe in settings that they didn't quite anticipate. So that sort of ensured me in terms of that this is a worthwhile effort to think about BIC, because the Bayesian model averaging package that Adrian Raftery, for example, has is based on the averaging is done on BIC, and various other types of, when it seemed like I could load off work on other people and do numerical experiments, I saw posterior probabilities being reported. Very often it turned out that these are just BIC-based approximations and not the marginal likelihood that I wanted to compare my criterion to. So from that perspective, I think it remains somewhat numerically tough to compute marginal likelihoods in any reasonable accuracy. And I think we have very good methods for it, and better, but they still require some, I think, tuning to the problem. So if we think about producing a piece of software, I think there's some appeal in this sort of BIC, in these BIC type proxies. Okay, now I don't know enough about what's under the hood for the focused information criterion, but I thought that would be interesting, and I think that implicitly came up, for example, in the last point, right? There was what exactly are we going after, and to what extent we can tune model choice to that, I think is interesting, but I don't have anything much intelligent to say. I'm not sure whether you have. I think that's an interesting thing to think about, but I don't think I can offer anything. Judith made a number of interesting comments. So one that she sort of let us get away with that I think is actually quite strange in a way. So the marginal likelihood of a model is defined in isolation, right? You can posit a model, a prior, and you can integrate the likelihood function, and that's it. And then we do all this stuff where we think about other models that are also under consideration, and we try to think about model uncertainty and what that means in terms of when we think about these approximations we're going after. It would be nice to also have an information criterion in which we don't do this explicit referencing other models and this averaging. That would be very nice. But I think we're not there yet, at least mathematically. So what would be needed there would be some way of getting an asymptotic expansion that would be uniformly valid. So for us it would mean that we say some series expansion, maybe with coefficients that depend on the unknown data generating distribution, that would be accurately approximating the marginal likelihood with an error that is bounded uniformly as I vary the data generating distribution. So this would of course be much closer to what finite sample behavior actually is, and if things depend continuously on the data generating distribution, we can maybe plug in an estimate and get something very good. But as far as I know, there's discussion of uniform expansions in textbooks on univariate Laplace integrals, but I don't think we're anywhere near to the things that we want to do in statistics when we think about a marginal likelihood. And so from that perspective, I view our proposal also as, in some ways, we're doing a little bit of capturing what would need to be happening in a uniformly valid approximation to a marginal likelihood through our averaging, even though this has the side effect that now as defined, things will change potentially if you drop a submodel of the model that you're considering, that you want to define a score for, an information criterion for. If you drop that from consideration, then that'll have an effect on the way we define our criterion. The log n issue, I think that Judith mentioned. She mentioned this paper by Elisabeth Garcia and Ramon van Handel. Did I get this right? So there is some. So our consistency theory is sort of as crude as it gets. It's about statements in probability and pairwise comparisons of models. So there has been more refined work that looks at almost sure statements versus statements in probability, and takes a much closer look at how the likelihood functions of the various models that we consider behave. And and so I think if there's any hope at addressing the comment by Richard Charnigo on maybe not having a fixed upper bound on the number of mixture components or so, we would have to turn to work like that and see whether that can be adapted. But I'm not sure, because we're at the log n level there, I think, right? And so that might not be possible quite like that, but we would have to look for at work like that. In terms of using bounds, so I would say so the groups around Watanabe, they've been sort of world champions, I guess, in obtaining some concrete results on what these learning coefficients actually are and what their multiplicities are. But in terms of more general, in mixture models, in terms of more general mixture models, I think that sort of, I guess, as far as I can tell, the tightest bounds that we know about are from Judith's paper with Kerry Mingerson that was in JRSSB. So that's what we ended up in the last version basing our experiments on. And I think bounds are actually not necessarily that complicated to obtain. I mean, we're very happy to count parameters, right? So you're very happy with determining the dimension of the set of matrices of Lie at 6 by 7 that has rank 2, right? It doesn't bother you, right? I think it's only trivially more involved to think a little bit then also about if you have a map that is infinite to 1, what is the dimension of the pre-image? Is something that you can often, I think, work out. And it's mildly more complicated than parameter counting, I would say. And that gives you very non-trivial bounds, I would say, that would actually make our criterion different from BIC. So I think I'm actually quite positive in terms of there being non-trivial bounds available for use in our criterion that would make it quite a bit different from BIC. I don't know, do you have any comments about computation of marginal likelihood?
I can say a couple of words.
I'll come back to say more.
Okay. Now I'd just like to reinforce what Mathias said about the difficulty of computing marginal likelihoods in practice. So there is nested sampling as a general method for a Monte Carlo method that will give you the marginal likelihood as a natural product of the calculations. And this is used in astronomy, but I'm not really sure if it's used much outside of that field. Otherwise, we've got reversible jump, Markov chain Monte Carlo, and as far as I know, there are only 2 really reusable implementations of that. There is the software that accompanies the paper by Green and Richardson on mixture models, and there's also an implementation of reversible jump for variable selection in OpenBugs. But apart from that, there's not really much software out there to do the calculations. And finally, there's also path sampling, which is I've tried in some of my own work and found extremely difficult to implement. So I think the ease with which marginal likelihoods can be calculated in practice should not be underestimated. I'll hand back to you.
Another important point, so something that I didn't mention at all in the presentation was what are the assumptions underlying Watanabe's theorem. And so I think the one that makes the strongest disconnect between what we think about and what is under the hood is that assumption that Judith mentioned of the parameter space being compact. And in Watanabe's theory, that comes from, if you have a compact set, you can cover it up with little neighborhoods and you can do local analysis. So that's where the importance of that comes in. So there are some models, like factor analysis, sometimes these pre-images that you have to think about in the parameter space, they are compact. Boom. End of story. So there's nothing you have to worry about, really. It's not an assumption. It's just a property that we have. But in other cases, like mixture modeling, you do have that. So you do, in principle, the theorem is disconnected from anything you do unless you would work with compactly supported priors and so on. Or at least, priors that considerably exponentially small, maybe in tails. So that is something important. But so there's also a connection then to if if you don't somehow rein in a little bit the parameters, you also see that likelihood ratios don't necessarily need to be bounded in probability. There's this classical Hardigan paper that shows that for Gaussian mixture models. And so we haven't pushed this at all in the paper, but I think it would be interesting to pursue a little more to what extent one might use map estimates opposed to maximum likelihood estimates in criteria like we're proposing. We put in maximum likelihood estimates everywhere to sort of stay true to Schwarz's criterion and generalize that honestly. But I think it could be interesting to consider map estimates where you carry a prior along as you fit models, and also involve that then in when you approximate the true likelihood, right? What else? In BIC, I think so. My colleague Adrian Raftery, and I think likes to point out often that so the BIC, you can sort of work back what would be the prior that gave you BIC exactly, right, as a marginal likelihood. And so there's this notion of a unit information prior. So yeah, I don't see like anything like that would be. I don't have anything to offer there in the singular world, and not to speak about why this should be a reasonable prior in any way. What else? Yeah, so I'm grateful that somebody brought up the WBIC, I guess two contributors. I think it's really quite an interesting method. It's, I'm not sure I'm saying this right, but so marginal likelihood can be calculated by thermodynamic integration. And you can think about a mean value theorem there. And it turns out that you can show that asymptotically, where the function value is equal to the integral, is going to be related to 1 over log n, and that's what we saw on one of the slides by Toro Imai. And yeah, and so that provides a way with sort of through the mean value theorem and thinking about thermodynamic integration, you can get an estimate of the marginal likelihood based on posterior simulation under power, sort of a power posterior where power is related to log n. I thought that was a very interesting paper of Sumio Watanabe's, and it's nice to see this explored a little bit more. I didn't know about all the details of how it played out. We put it in for comparison based on a referee's comment, but it's actually quite different from what we do. So it explicitly involves the prior. So when we made a comparison, we had to put in a prior. And there's a Metropolis Hastings sampler that runs, and so that had to be tuned. And maybe possible that you can get better results than we show in the paper by spending more time on tuning this. I spent some time on it. It's not easy to, without getting lost to start, you have to tune these samplers for all the different models, and so there's a lot of things going on. So I tried to, in the comparison, stay as close as possible to code that Sumio Watanabe used in a paper of his. But I think it's a very interesting method in which the prior is very actively involved, and if we make the prior important enough, it should be that this WBIC can also look very good compared to what we propose based on asymptotics. So I think it's entirely different in some ways when you might want to use that, I think. And anything else? Yeah. Another interesting point that came up was this critique at our averaging is always, you think about a model and submodels. Okay? So that turned out to give this a convenient triangular system for which we can actually certify that there's a positive solution and a unique one. So that was very nice. By doing that, we also sort of stay away from any asymptotic theory for models that are false. So we only then invoke theorems about when models are true. Now, maybe we should think about, when I think about a 3 mixture, maybe I should think about what happens if that truth is a 4 mixture, right? And that would be perfectly fine. I see sort of 2 obstacles to that. So one is as you write down our fixed point equation system, this will be just some square polynomial system that's complicated. And we've played with this a little bit, but as of now, I don't have a good way of saying anything about what sort of solutions you get. So it's something we're going to hammer a little bit more, but it was difficult to get at that. And then it's also not always clear. So Watanabe's theorem, as presented and developed in his book, it assumes that the truth is inside the given model that's considered. And it need not be the case that, let's say, a normal mixture model has a nice asymptotic expansion if you generate data from a gamma distribution. It's not clear. Yeah? And so it's not clear that if you go sufficiently wrong, it's not clear that there is an asymptotic expansion, that there is any version of sort of this Schwarz theorem that motivates BIC. So in our work, we sort of stayed away from considering explicitly false models. I think in practice it's maybe not as bad as it looks, because if there are models that are sort of overwhelmingly false, you're going to figure that out pretty quickly just from the likelihood term. And so they will not get much weight. They will not get involved in averaging that we can consider. And so I think it's, from a practical perspective, not as bad as it looks. But from a conceptually, there's a little bit of a, us focusing on models being true, there is maybe a little bit, one can definitely critique that. I think that's fair. I think, I've mostly, I didn't follow all the points. There were some points about selecting a single model where, I think it's clear how we would average, at least, do model averaging. And I don't really want to say much about if somebody wants to predict, then, we had also in this sort of series of discussion papers that talk about how prediction is different from, identifying some true structure that you hypothesize is there. And so I think this is simply different tasks, so I don't think too much interesting can be said about that, so I won't try and say anything there. I think I think that's about it, what I can remember right now. So, did you have anything more to add? I don't know whether I should add anything to that. I just, one point, I don't think it's necessarily a weakness of the singular BIC that it depends on what other models are under consideration, because if you consider the circumstances under which one might use the marginal likelihood and calculate posterior model probabilities, you're already in an M-closed situation where you have a given set of models of which you are assuming one of them is actually the true data-generating model. So since we're already working within that context, I don't see any difficulty in the fact that the singular BIC really depends on the total set of models under consideration, but that's just that could be considered a philosophical point of view. Well, it's a shame you didn't get to talk about the latent class analysis, but so there's no point. But otherwise, I would have said something